Welcome back. Let's get right into this explainer. We're diving into the invisible but absolutely massive force of magnetism. We interact with this stuff literally every single day, right? From the tiny magnets inside your earbuds to the massive fields that literally protect our entire planet. It's a huge deal. So today, we're going to scaffold our way up. We'll start with those classic bar magnets you've definitely seen, and we'll scale all the way up to the massive industrial electromagnets used in heavy engineering.
Here's the roadmap for today. We'll start with permanent magnets and poles, then break down hard versus soft materials. From there, we'll map out how to actually visualize these invisible magnetic fields. Then, it's time to scale way up to the Earth's own magnetic field. And finally, we'll wrap up by creating our own power-on-demand electromagnets.
Section 1. Permanent magnets and poles, the rules of attraction. Let's lay the groundwork. So the fundamental rule of magnetism, and this is something you just cannot negotiate with, is how poles interact. Like poles repel and unlike poles attract. It's really that simple. If you try to force two north poles together or two south poles, they're going to actively push each other away. But if you bring a north and a south together, boom, they pull towards each other. It's the classic opposites attract scenario.
Now here's a fun question. How does a regular fridge magnet stick to the fridge door if the door itself isn't a permanent magnet? Well, it all comes down to induced magnetism. When you bring the north pole of a permanent magnet close to an unmagnetized piece of steel, like a pin or your fridge, it actually induces a temporary south pole right there on the nearest surface. And since we know opposites attract, the pin just snaps right to the magnet. The really cool part? Pull the permanent magnet away, and the pin goes right back to being plain old unmagnetized steel.
All right, Section 2, hard versus soft magnetic materials. Because, as it turns out, not all ferrous metals act the same way.
We generally classify magnetic materials into two camps, hard and soft. And no, we're not talking about how they feel. Hard magnetic materials, like steel, are pretty tough to magnetize initially. But once you do, they hold on to that magnetism incredibly well. That's exactly why we use them to make permanent magnets. On the flip side, we have soft magnetic materials, like soft iron. These guys are super easy to magnetize, but the second you take the magnetic field away, they lose their magnetism instantly. As you're going to see in a few minutes, that quirk makes soft iron absolutely perfect for electromagnets.
Moving on to Section 3, visualizing magnetic fields. Let's look at the invisible mechanics behind the magic.
This is one of my absolute favorite ways to actually see what's going on. When you sprinkle iron filings around a bar magnet, they physically align themselves along the invisible magnetic field lines. And notice where they're clustering the most. Right there at the two poles. That visual density is a direct map of the field's strength. Basically, the thicker the cluster of filings, the stronger the magnetic force in that exact spot. Now, while iron filings are great for a quick visual, if we want to accurately map these forces in a lab, we have to be a bit more precise. We use a small plotting compass. The process is pretty straightforward. Place the compass in the field, mark a dot at the tip of the needle, move the tail of the compass to that dot, and just keep repeating. This lets us trace the exact path of the magnetic field lines. And remember, the universal convention in physics is that these lines always travel out from the North Pole and curve around into the South Pole. Look at the sheer difference in how these fields interact. On the left, we've got two opposite poles attracting. Those field lines connect almost like stretched elastic bands, physically pulling the two magnets together. But on the right, with two like poles, they're repelling. The field lines are quite literally compressing and pushing against each other. You can actually see that distinct, empty dead zone right in the middle, where the two opposing magnetic fields just cancel each other out. So seeing how these field lines control movement naturally leads us to a pretty massive question. If a compass needle is just following magnetic field lines from north to south, why does a freely suspended compass needle always point roughly towards the Arctic? Which brings us perfectly to Section 4, Earth's magnetic field, the giant inside. To understand your compass, you have to realize that our entire planet acts as if it has a gigantic bar magnet jammed right through its core. Earth generates this enormous magnetic field that stretches way out into space. And honestly, we are super lucky it does. This field isn't just for navigation. It acts as an invisible shield that deflects the solar wind, which is this highly destructive stream of charged particles constantly blasting out from the sun. Without it, our atmosphere would be toast. But here is the part that twists everyone's brain the first time they hear it. If the North Pole of your compass needle is being pulled towards the Arctic, that actually means there must be a magnetic South Pole sitting up there near the Earth's geographic North Pole. Think back to our first rule, opposites attract. So for your compass's North Pole to point north, it literally has to be seeking a magnetic South Pole. Crazy, right? Okay, final stretch. Section 5, Creating Electromagnets, How We Get Power on Demand.
Remember those soft magnetic materials we talked about? Here's where they shine. We can build something called a solenoid. It's essentially a specialized coil of wire, usually copper, that instantly becomes a magnet the moment you run an electric current through it. Flip the switch on, boom, you have a powerful magnet. Flip it off, and the magnetism vanishes completely. When the current is flowing through that coil, it generates a magnetic field pattern that looks almost exactly like the permanent bar magnets we mapped out earlier. One end becomes the North Pole, the other is the South, and those field lines loop all the way around and run straight through the empty center of the coil.
What makes electromagnets totally game-changing is that unlike a permanent magnet, you can crank up their strength whenever you want. You got 3 main ways to do this. Number 1, just pump more electric current through the wire. Number 2, increase the number of turns on your coil. Packing more loops into the same space really concentrates a field. And number 3, slide a soft iron core right down the middle of the coil. That iron gets magnetized by the field and dramatically amplifies the whole setup.
And this brings us to the real-world application. Think about those massive scrapyard cranes lifting tons of solid steel. They use gigantic electromagnets with soft iron cores. The operator hits the juice, the magnet picks up immense weight, swings it over to a pile, and then, just by cutting the current, instantly drops the payload. If they used a permanent magnet for that job, that steel would be stuck there forever.
So let's wrap up with a thought experiment. We know we can instantly flip an electromagnet's poles just by reversing the direction of the current. Well, if the Earth is basically a giant magnet powered by molten currents in its core, could our planet's massive magnetic field ever reverse its own poles? The mind-blowing answer from the source data is yes, it absolutely has. Geologists have found that the Earth's field flips roughly every 300,000 years or so, with the last one happening about 780,000 years ago. So the real question is, when is the next flip coming? And how is our completely electricity-dependent society going to handle it? Definitely something to chew on. Thanks for joining me on this explainer, and keep exploring.